So we do need to be careful whenever we come across two data sets. It does not necessarily mean we have a two-sample procedure. There are cases where our data sets are not independent from each other, but rather paired, where each data point is directly connected to another data point. And so rather than treating them as two sets of measurements, what we're more interested in is looking at this single set of differences between each pairing. And so that's one thing we want to look for is how are these two groups completely independent from each other, or are they what we call paired? So some examples of things that are paired are, what if we have a before and after, where we're measuring the same person before some treatment and after some treatment. Well, that means those data points are completely directly linked to each other, and we don't want to compare one person to another person, but just to their own scores. Twins are another option, often used type of thing in scientific studies, where we want to compare the twins to each other. So even though we have two sets of measurements, we're going to directly compare them to each other. Maybe we might have things like left and right hand, or husband, wife. So there's lots of different things. These are just a small set of examples of when things are paired. But if you can find that direct connection from one point to another, then we want to also make sure that we're using a paired type of procedure instead. Now, what is a paired procedure? It actually becomes equivalent to a one sample type of procedure. So one sample t-test. So how is it equivalent is when we find these differences between the two pairs, we're left with one set of data, which is one set of differences. And then we can just make sure that we understand that, okay, we're performing a test on that one pair of differences, one set of differences. And so if we ever come across that, just know it's really the same exact thing. So let's just look at an example though, so you can see. Here we have listed below our systolic blood pressure measurements taken from the right and left arms of the same woman. So this is, for example, woman 1, second woman, third woman, fourth, and the fifth. And so we have these things are paired together because I don't want to compare this woman here to this person over here because they're different people. But I want to make sure that we compare them directly to each other. And so the way we do that again is we find their individual differences between each of these. So I may do each one like left minus right. I'll just write that down. Left minus right. 115 minus 102, which gives me 13. Here we get like negative 2. Here I would get 18. Negative 1. And 21. And so basically we turn these two data sets, left arm and right arm, into a single list of differences. A single list of differences, and that's what we're going to do it on. So let's go through the 5 steps and see how these work out. First, we have to write our hypotheses. So our null and alternative, gonna be not two separate values. We don't have two separate parameters since we don't have two independent populations. What we do have is a single set of differences. So the way we do that is we actually write mu for the single set of differences, and a lot of times we either put diff or d to represent the differences, that it's a difference between two sets of data. Now, one thing we do take from the two sample things is if there are no differences between the left and right arms, then that means we would have a subtraction difference or a mean of all these differences to be 0. So for paired tests, often we are looking at equal to 0 here as well. And in this case, we're just trying to see, is there a difference? Well, anything that's not equal to 0 would mean there is a difference. So this is how we write our hypotheses for a paired t-test. So second, what is the name of this? This is actually what I just said. We call this a paired t-test. So again, it is technically being it's a one sample t-test on the pairs, on the differences from these pairs, but we call these a paired t-test. Step 3, since this is equivalent to a one sample, we don't have to look at these separately. We only have to treat the differences as our single sample. So when we're checking these conditions, that's one thing we have to be careful of. So I'm just going to check the large enough condition again. And as we can see, 5 is definitely not greater than 30. So it looks like we failed a large enough condition. How do we get around that? Again, we can make sure we look at a graph. So I've just constructed a very quick dot plot right here. And it does look like there's quite a gap here, but for the most part, I don't see any super heavy skew or any crazy outliers compared to this. So even though we may be hesitant to do this, we'll say it does look not skewed and no outliers. So finally, now that we have that, we can go on to step 4, which is our calculations using technology. Now, one way we can do that, again, is we can just use this as our single list and treat it as a one sample t-interval. But StatCrunch has a way of doing this also when we have our two lists. So I didn't actually have to do this by hand. So as you can see, I have the two data sets from the left and right arms listed here. If we go into t-stats, because it's still working with means, and then you'll see actually we have one called paired. And we can select the first sample minus the second sample. Since we did left minus right, make sure you put the left first and the right second. And this is something I'll click, differences. What does this do is you'll see that these values here that I calculated by hand, it'll calculate those for us. The hypotheses, it's already what we wrote down, so that's looking good. And we can do compute. And there we go. So you'll see that right here, it included the differences that I calculated already. And now it gave us everything we needed, including the mean of our differences. So the mean of all these things was 9.8. And this is, again, what we're interested in, though, is what's that test statistic, what's that p-value. So let's go ahead and take a look at that. 2.046 is our test statistic. And then finally, our p-value was 0.1102. Finally, we can write our conclusion based off of this. And it says we're going to use an alpha of 0.01. And clearly, 1102 is not less than that. So our last step, since the p-value is greater than 0.01, we fail to reject H0. So there is insufficient evidence to show a difference between the measurements in the two arms. Just so you can see how this is equivalent to doing a one sample test here, we can do the similar thing on these differences that we calculated here. So rather than doing the paired, if I wanted to, I could have done t-stats, one sample. We do have the data still here. Rather than mu d, it's just mu, but it's the same thing. And if we do compute, you'll see that we get the identical results for everything that we got here. Oops.